Welcome back to LabRat Scientific. Now, in a previous episode on orbital mechanics, I described satellites as being objects that are continuously free-falling towards the Earth, but due to the curvature of the Earth and the satellite's horizontal velocity, they miss the Earth as they fall. Now, what I want to do in this episode is talk about what I meant and also introduce the concept of centripetal force and how it applies to describing satellite orbits. Now, as usual, I want to start off with some physics, and then I want to do a demonstration to support the theory. So let's go ahead and get started. We can view orbits from two different perspectives. First, from a geometric or physical perspective, where we view the orbiting body as continuously missing the Earth as it falls towards the Earth due to that object's horizontal velocity and the Earth's curvature. Or we can look at it from a pseudo-force perspective, where the pseudo-centrifugal force created by the object's orbital velocity exactly balances the inward force caused by Earth's gravity. Now, I refer to the centrifugal force as a pseudo-force because in reality, that outward force does not exist, but I'll explain that later. Now, there are a few basic concepts we need to keep in mind. First of all, a satellite remains in orbit because of Earth's gravity. If there were no gravity in low Earth orbit, the satellite would simply fly off into space along a straight line. Now, the gravitational force between two bodies is a function of the distance between them. The greater the distance, the less the gravitational attraction. And also, the term zero-g used in conjunction with a vehicle in orbit is a misnomer. There is actually gravity in orbit, it's just that everything is in free fall relative to everything else, so everything just floats around like there's no gravity, hence the term zero-g. Now, the term free fall used above implies that everything in orbit is falling, and this is exactly correct. A satellite in orbit, and even the moon, is falling or accelerating towards the center of the Earth. But if the objects have enough horizontal velocity, they'll continuously miss the Earth as they fall. Now, as stated earlier, the acceleration due to gravity is a function of the distance between the two objects. Now, in the case of the Earth and the satellite, it's a distance between the center of the Earth and the satellite itself. Now, we usually reference satellite orbits relative to the surface of the Earth, so the graph at the left shows the acceleration due to gravity as a function of height above the Earth's surface, ranging from 0 nautical miles to 1,000 nautical miles. And the equation below shows how you calculate the acceleration due to gravity as a function of height above the surface of the Earth. Now, acceleration due to gravity is equal to the gravitational constant divided by the radius of the Earth plus the orbital height squared. Now let's take a closer look at orbits from what I call the geometric perspective. Now, for this example, I'm going to assume that the orbital altitude is 200 nautical miles above the surface of the Earth. Now, note that I'm using nautical miles instead of statute miles. There are 6,080 feet per nautical mile. And the calculated orbital velocity at that altitude is 25,200 feet per second. Now, in this process, what I'm going to do is I'm going to calculate the amount of time it would take the satellite to fall straight down that 200 nautical miles. I'm going to take that fall time and then using the orbital velocity, calculate how far the satellite would move in the horizontal direction. And then I'm going to plot the horizontal distance and the vertical distance and see if that satellite falls on this purple line. And then do that for a couple points to see if the satellite tracks along the desired orbital path. I'm not going to go into detail here, but here's my calculus. Velocity is the integral of acceleration, and distance is the integral of velocity. I go through the mathematics and I get the distance the satellite falls is equal to 1/2 acceleration due to gravity times t squared. If I apply some basic algebra, I can see that the time to fall that 200 nautical mile distance is the square root of 2 times the distance divided by acceleration due to gravity at that altitude. Here's my equation once again. Here I'm calculating the distance the satellite will fall, 200 nautical miles times 6,080 feet per mile. That gives me 1,216,000 feet. Now, the acceleration, as I pointed out earlier, is not quite 32.2 feet per second squared at that altitude. It's actually 29.1 feet per second squared. So if I take the average of those two, I can use the acceleration of 30.65 feet per second squared. Plug those numbers into the equation, and I see the fall time would be 281.5 seconds. Now, if I multiply that fall time times the horizontal velocity of the satellite, or the orbital velocity, we can calculate how far the satellite will move in the horizontal direction. And you see that math here. You'll see that the distance the satellite moves in the horizontal direction is 1,167 nautical miles. Now, if I plot the horizontal distance and the vertical distance, I can get the total displacement of the satellite. Now I can attempt to graph this information on a piece of graph paper. So here's my crude graph, and you have to remember that this is not precise, so everything won't line up perfectly. It'll give you a good idea of the process I'm using. So I'm using a 200 nautical mile by 200 nautical mile reference square. So again, that's the distance the satellite is above the Earth's surface, so it's about 1 square. Now, if I calculate the number of squares required to cover 1,167 miles, you'll see that equates to 5.8 squares. So that's represented by my yellow line here, so that's roughly 5.8. Now I want to superimpose the free fall, the downward towards the center of the Earth fall of a satellite of 200 nautical miles. I superimpose my square here. So you see roughly where the satellite will fall after that 280-second travel time. Now I can repeat that process and show that the satellite tends to track the desired 200 nautical mile dashed line on my graphic. Again, it's not perfect, but it's a close approximation. So let's do a little sanity check. What would it look like if a satellite were only traveling at 10,000 feet per second? So what I can do is I can calculate the horizontal distance the satellite will travel. Again, that's at 281 seconds times 10,000 feet per second. I ultimately come up with 462 nautical miles. I divide that by 200 nautical miles per square. I come up with 2.3 squares for horizontal distance. So I plot that over here on my graph. That's roughly 2.3 squares. And the satellite's going to fall towards the center of the Earth 1 square. So you'll see that the satellite would actually hit the surface of the Earth if it were only traveling at 10,000 feet per second. So that gives me a reasonable sanity check. This process will actually show that if the velocity is too low, that the satellite won't stay along that purple dashed line. So it looks like the geometric description of why satellites follow curved orbital paths is valid. Now let's take a look at a description that involves the balancing of the centripetal forces and the gravitational forces on a satellite. Now before we get started, let's make sure you understand the concepts of centripetal and centrifugal forces. Now here's a simple diagram of the system. I've got my red ball here, and I want to make it follow this curved circular path centered around this blue center point. Now, if I apply a force to the ball, Newton says that ball will accelerate and start moving. However, it's going to move in a straight line. Now, in order to get the ball to follow the curved path, I'm going to have to apply an inward force towards the center of the circle. Now, this inward force is known as the centripetal force, and it will make the ball follow the curved path. Now, this inward force could be supplied by a string or maybe gravity if we're talking about satellite orbits. Now, this force puts the string in tension. So the string is pulling on the ball, but the string is also pulling on the center of the circle. Now, from the perspective of the center point, it feels as if there's an outward force acting on it. So this is where that apparent or pseudo outward acting force originates from. Now, that pseudo force is equal and opposite the centripetal force that is keeping the ball moving in the curved path. Now, if the string is cut, the inward centripetal force and the pseudo outward force both go away, and the ball will once again begin to follow a straight path. So, as long as there is an inward centripetal force acting on a circling or orbiting body, we can treat the problem as if there's actually an outward centrifugal force. Now, this outward force is caused by the velocity of the ball or satellite and its distance from the center point of rotation. Now, when talking about a satellite in orbit, the outward centrifugal force is balanced by the inward force provided by gravitational attraction, otherwise known as weight. Now let's take a look at the equation for centripetal force. This is the force acting inward on the ball towards the center of curvature. And the centripetal force F is equal to mv squared divided by r, where m is the mass of the ball, v is the tangential velocity of the ball, and r is the radius of curvature. Now Newton says if there's a force acting on a moving body, then there must be some sort of acceleration present. So we can look at Newton's second law, F equals ma. And by equating the two equations above, we can determine an equation for rotational acceleration. So here you have m times v squared divided by r, and also m times acceleration. Again, equating those two equations, we come up with an equation for rotational acceleration of a is equal to v squared over r. Now, let's do a simple demonstration to see how the ball moves when the centripetal force is present and when it's not. Here are some still images of the demonstration. See the ball moving along the curved circular path a few moments later. And here it is at the release point. And you can see that the ball then moves along a straight path after the centripetal force is removed. As you can see from that simple demonstration, it proves that the ball will move along a straight line that's tangent to the curved path once the centrifugal force is removed. So hopefully some of that makes some sense. Now let's take a look at the math that's associated with centripetal forces and gravitational force. Once again, here's the equation for centripetal force. F is equal to mass times velocity squared divided by the radius of curvature. Now let's assume a satellite weighs 500 pounds at the surface of the Earth. To determine the mass, we have to divide by 32.2 feet per second squared, which is the acceleration of gravity at the Earth's surface. We go through the math, we see that mass is equal to 15.5 slugs. Next, we need to calculate the radius of curvature, which is going to be the radius of the Earth plus the orbital height above the Earth's surface. We plug in our numbers, and we see that the radius of curvature, r, is equal to 22,116,000 feet. Again, that's above the Earth's center. Now, we can calculate the centripetal force by using the equation F is equal to mass times velocity squared divided by the radius of curvature. We plug in our numbers, and we see that the centripetal force for this orbiting satellite is 445 pounds. Next, we calculate the gravitational force, utilizing the equation F is equal to ma. Now, this is the gravitational force or the weight of the satellite at altitude, 200 nautical miles high. We don't use 32.2 feet per second squared. We use g at 200 nautical miles high, which is 29.1 feet per second squared. We go through the math, and we see that the gravitational force, or the weight of the satellite at altitude, is 451 pounds. Here are those two forces displayed on a simple graphic. I have my gravity force acting downward, 451 pounds, and a centrifugal force of 445 pounds pointing outward. Now, the difference in these numbers is approximately 1%, and that's due to the use of approximated numbers and rounding off values in the calculations. But for all intent and purposes, this shows the gravitational force and the centripetal force are balanced when the satellite is at required orbital velocity. So, in conclusion, both explanations describing why a satellite follows a curved orbital path are valid. Well, there you have it, at least two plausible explanations on why satellites follow curved orbital paths. There's a geometric perspective where you look at the horizontal displacement and the vertical displacement. Then there's a perspective to where you look at the balancing of the centripetal forces with the gravitational forces. And you can always go to LabRatScientific.com and learn more about this topic and others. Well, that'll do it for this episode. I hope to see you next time at LabRat Scientific.